All right, let's talk about a secret weapon. A really powerful technique that honestly is behind some of the fastest software you use every single day, but it's often kind of misunderstood. We're diving into memory mapped files.
You've probably felt this, right? I mean, we've got these incredible SSDs, tons of RAM. Everything should be lightning fast. So why does reading and writing files still manage to slow our high-performance apps down to a crawl? Well, what if I told you the problem isn't all what you think it is?
You see, the real villain in this story, the thing that's slowing everything down, it's not your disk. Nope. It's something way sneakier, happening deep inside your operating system every single time you do a traditional file read. That's it right there. The performance killer is the process itself. Every time your application asks for a piece of data from a file, the system is just constantly making these redundant, time-wasting copies. It's like making a photocopy of a photocopy. You just keep losing time and quality with every step.
Okay, so let's break down this little dance, this shuffle. Your app says, hey, I need some data. The OS kernel goes, sure thing, and it reads the data from the disk into its own private memory space. But here's the catch. Your app can't see it there, so the kernel has to do it all over again. It makes a second copy, this time from its memory into your application's memory. And that second copy, that is pure 100% wasteful overhead.
So how do we get around this mess? There's got to be a better way, right? We need a totally different approach, one that just stops all this copy shuffling and instead draws a direct line to the data. And that, right there, is where memory-mapped files come into play.
Okay, that sounds pretty technical. So what does it actually mean? Well, a memory-mapped file, or an MMF, is basically this really clever trick. You just tell the operating system, hey, see this file on my disk? I want you to just pretend it's already part of my application's memory.
And this is the absolute key. Instead of going to the kernel librarian and asking him to go fetch a book and bring you a photocopy of a page, you're asking for a map of the library itself. You get a direct pointer, a direct address to where that information lives, and you can just access it like it was in your hands the whole time. And this comparison just lays it all out plain and simple. On the left, you've got the old way, a bunch of system calls, data getting copied here, then copied there. It's a lot of busy work. And on the right, the new way, one single setup action that creates a direct virtual link. It's clean, it's elegant, and it is so much more efficient. So what do we actually get from all this? What's the payoff? Well, this is where it gets really exciting, because when you map files to memory, you unlock a whole set of what I like to call superpowers for your high-performance systems.
The amazing thing is how these benefits all stack up. Yeah, zero copy access, that's the big headline. But that also means fewer system calls, which cuts down on overhead. And get this, you get to piggyback on the operating system's own super smart caching and prefetching logic for free. This makes it just incredible for handling files that are way bigger than your available RAM.
This is it. This is the magic number. The whole point of this entire exercise. 0. That's how many redundant data copies happen between the kernel and your application. The data gets read from the disk into the OS page cache one time, and your app gets to look at it right there. No extra shuffling, no wasted effort. And believe me, this isn't some obscure little trick. This is the bedrock, the foundation of performance for the biggest tools you use every day. We're talking high-performance databases, massive search indexes, huge data analytics platforms. They all rely on memory mapping to get the kind of speed and scale they need. Now, as amazing as all this sounds, let's be real. It's not a silver bullet, it's not magic. This is a powerful tool. And like any powerful tool, it comes with its own set of rules and trade-offs. You really have to understand how it works to use it right. So where can this go wrong? Well, if your app is constantly writing lots of tiny, random bits of data, it might not be a great fit. Or if the file itself is always growing and shrinking, the overhead of managing that memory map can actually start to slow you down. It really shines with read-heavy workloads on big, stable files.
And that really gets to the core of it. You can't just sprinkle memory mapping onto a badly designed system and hope for a miracle. It's not a shortcut. It demands that you think about your architecture, your data structures, and how you access them right from the very beginning.
Which brings us to, I think, the most important takeaway of all. This isn't just another performance hack to add to your collection. It's bigger than that. I absolutely love this quote because it just nails it. It forces you to completely change your perspective. You stop thinking of a file as this thing you have to open and read from and then close. Instead, you start seeing it for what it can be, a massive extension of your application's memory. And when you're building systems where the data is just gigantic,
where it completely dwarfs your available RAM, this model of treating the disk as memory becomes absolutely essential. For the biggest data challenges out there, it's not just the fastest way to do it. A lot of the time, it's the only way that actually works.
It kind of makes you wonder, doesn't it? For decades, the rule was that you had to copy data to read a file. But by challenging that one basic assumption, we unlocked a whole new level of performance. So it leaves you with this question: what other fundamental rules of computing are just sitting there, waiting for a new way of thinking?